Welcome to this presentation on the numerical integration of the method of characteristics on the Hartree method. In an unsteady open-channel flow, the Saint-Venant equations are a system of two equations to solve one-dimensional unsteady flow motion, for example for fluid modeling. One equation is a continuity equation, and the second one is a momentum equation. The method of characteristics is a mathematical technique for solving the differential form of the Saint-Venant equations, analytically, graphically, and numerically. Herein, the numerical integration is discussed. The following three photographs illustrate the same river at three locations, moving downstream up to its estuarine zone. The differential form of the Saint-Venant equation may be transformed into a characteristic system of equations shown here, in which v is the velocity and c the celerity of a small wave. Physically, the forward and backward characteristic trajectories correspond to the path followed by small disturbances propagating in a channel with a current V. For an observer traveling along the forward characteristics C1, the first equation is valid at any point. Similarly, for an observer traveling on the backward characteristic, the second equation is valid. And this is illustrated on this sketch here, showing the characteristic diagram. A simple numerical integration of the characteristic system of equation is the Hartree method. Sketch here. The Hartree method uses fixed time and spatial intervals. During the linear interpolation, the time step must follow two conditions called the Courant condition or CFL condition. The Courant number must satisfy the Courant condition, and the Courant number represents a measure of how much information traverses the computational grid in a given time interval. The Courant condition is necessary for the stability of explicit finite different methods, such as the Hartree method. It means neither damping nor amplification of surface perturbation. For completeness, the numerical stability of implicit finite difference scheme is superior, yet explicit schemes do have some advantages. Back to the Hartree method, it is assumed that the flow properties are known at a given time step. At the next time step, the characteristic trajectories intersecting at the point M are then projected backward in time, intersecting the previous time step, point L and R on the sketch. The location of the point L and R are unknown beforehand because they do not coincide with grid points. Their velocity and celerity must be interpolated linearly between point A and B for point L, and between points B and C for point R. This, in turn, enables the calculation of the velocity and celerity at the next time step at point M. The Hartree method is named after the English physicist Douglas R Hartree. The scheme is sometimes called the Hartree-Fock method, after a Russian physicist. The Saint-Venant equations and the characteristic system of equations are essential concepts for the numerical modeling of unsteady open-channel flow and its practical application, including flood modeling. These are discussed in the relevant YouTube video movies in the same playlist in the same channel.